The first thing is you'll remember the announcement of the fee for CW&E applications the other day. I want to make sure that everybody's aware because a few people came to me and said, we've got to pay that every year. It is not an annual fee, it's an application fee. So no CW&Es that are current CW&Es will have to pay that fee ever. They just have the same renewal fee they've always had every 3 years. So that's the first thing to make sure that you understand very clearly. The second thing to understand is the CWSA requirement for CW&Es. So for those that acquire a CW&E, any application submitted after January 1st, 2021 will require a CWSA certification in the packet and one external certification. So still 2 certifications outside of the CW&A track. And then for those who are CW&Es in the room, you will not be required to acquire the CWSA until you need the CEs from it and it on your list until you renew after January 1st, 2021. So if you renewed on December 31st, 2020, you wouldn't need it until December 31st, 2024, right? So it's would be your next, actually, I'm sorry, 23. It's your next renewal time after January 1st, 2021. So hopefully that clears up any confusion you might have had there. Well, we're going to do some fun things here today. We're going to talk about what I'm calling 10 and a half things you didn't know you wanted to know about wireless. But then in the process of this, I've got some goodies for you. And I have picked out some personal gifts that I want to give to you as we go throughout the presentation today. But here's the way we're going to do this. Whenever you see a number come up on the screen, and the number is a new number that you have not seen before, for example, moving from 0 to 1 or from 3 to 4, you want to shout out the number. The first person to notice it and shout it out gets the gift. Now, I will warn you, not every slide. That's not a new slide. See, you've already failed. Not every slide has a new number. Some are still on the same number. So you've got to pay attention. You can't sleep during the presentation and end up getting a reward. So you're rewarded for being awake and looking at the screen, at least the upper right-hand corner. Okay? So let's give it a try and see how you do. All right, very good. Now, it'll be harder than that in the future because you won't know that it's coming. You just never know when it's going to happen. See what I mean? It just changed from 0 to 1 and no one shouted it out. You have failed me already. So you've got to really pay attention because you just never know when it's going to happen. I could be right in the middle of a sentence. There, you're getting it. All right, that's how the flow goes. Okay, so make sure. Yeah, very good. So watch for the number changes. When you see the number change, shout it out, and I will have a gift for you. Now, there are how many things you didn't know you wanted to know about wireless? 10 and a half. And so therefore, there are how many gifts that I have for you today? No, 11. I'm going to go ahead and give you a whole gift. So you'll be okay with that. Now, what we're going to be talking about then is wireless, but one of the primary elements of the focus of my talk here today is going to be on the fact that we want to implement wireless solutions. We don't want to implement wireless. You know why? Because the universe already did that. So we don't need to implement wireless. We need to implement wireless solutions. In other words, if all we did was implement wireless, it would be like the emperor's new clothes, right? We could just go in there and say, hey, I'm done. Give me my $25,000 consulting fee. Actually, that's the business that I'm thinking about getting into. Implementing Emperor's New Clothes Wireless. I think I'll call it Emperor's Wireless. Oh, it's already taken, isn't it? So the point is that we want to make sure we have a wireless solution, something that actually solves a problem utilizing wireless communications technologies. And when you think of it from that perspective, there are a lot of things that are important in order to implement an effective wireless solution. And so we need to talk about many of those things here today. Oh, it was right over here, I believe. So Lex, we have right up here toward the front, a gentleman receiving a gift up here. Would you stand so he can see where you are right there, right on the end of the row? All right. So here's the first thing to keep in mind. Latency is. It's a physical reality that cannot be removed in communication links. It can be minimized, but it cannot be removed. Latency simply is. And when it comes to a wireless solution, we cannot just think of latency in terms of the link. And that's a big mistake that's often made. We can't even just think of latency in the terms that we in the networking world usually think of it. We think of it as packetization, serialization, geographic transfer, the range or distance of the links, in other words. These are the things that we think about when we think about what's going to impact the latency or the delay in my network. Well, that's fine because that is the delay in my network. But a wireless solution encompasses the whole end-to-end solution. It encompasses everything from some end device that has information to share with some other location. And then that other location may need to utilize that information, make a decision, and possibly communicate back with that end device with something that it needs that end device to do. So therefore, in our consideration of important delay and latency, we have to think about application logic as well. We can't just start at the network layer. Now you say, wait a minute, Tom, that's not my job, that's somebody else's job. Well, yes, but no. Because of the new world of wireless that we're finding ourselves getting more and more involved in. If you think about industrial IoT, for example, and the reality of sensor actuator devices that actually not only sense things in the environment, but then they make changes to behaviors, to processes, to machinery configurations, and so forth, then the reality is sometimes those changes need to be made near instantaneously. And if they need to be made near instantaneously, it is my job to know how long it's going to take for that decision to get made based on whether I go across the network all the way to the cloud, or if I just stay on my network, or if I just stay on my device. And so it does become important for me to consider where I'm going to perform processing. And this is one of the reasons why you hear a lot of talk about edge compute and things like this today, because of the importance of figuring out exactly where the processing needs to happen so that I get the results that I need in the time window that's required. Now, the reality is that some of you just took a deep breath right there. We have to think about the whole latency chain, right? So we've got to think about the whole latency chain. So we have here an example of a sensor. This happens to be an accelerometer. And so this sensor is able to detect movement. It's able to detect crashes, things like that. This sensor is going to talk to a gateway. We can calculate that, can't we? We have a way to calculate it because we can know the distance between the two devices. We know what the speed of light is in free space. We can get a very good calculated estimate of what the delay is going to be incurred from that link. We can even get an estimate of the delay due to packetization and serialization for that link. Then we've got the next link. We've got the link from the gateway, which happens to be a 4G LTE gateway, up to the cellular network. We can even calculate that, can't we? Because we can figure out how far our gateway is from the cell tower that it's synchronized with and utilizing, and so we can even calculate that delay. But then we get into the who knows world. How's it going to go across the operator's network? How's it going to, once it goes across that network, where does it actually have ingress to the internet? And then how far is that location that has connectivity to the internet from the actual cloud service provider that I'm using and where their servers are actually housed? And so all of that comes into the who knows realm. Yeah, we can try for service level agreements, but our cellular provider is not going to give us any SLE for our cloud, and our cloud provider is not going to give us any SLE for our service provider. So in this IoT world, there becomes a lot of who knows when we look at these calculations. And if who knows cannot fit into your time to decision algorithm, you can't accept that. You can't say, well, who knows when it has to do with a piece of machinery that if it doesn't stop moving, it could cause an accident, possibly even resulting in death. No longer is who knows acceptable. But instead, I have to have an instantaneous decision. And so it's very important we look at this entire latency chain that we remember that there are certain things you might have heard about lately that make you think, oh, that latest and greatest technology, that's the one that I want because it's going to really fix all of my latency issues and all of a sudden I'm going to be down to somewhere around 1 or 2 milliseconds in latency and therefore it's not going to be a problem. Now, I'm not going to say what that technology is, but there's been a lot of bragging about it lately. being able to do 1 millisecond or sub 1 millisecond. But, the reality is it's not just that point of the link that matters, is it? It's the whole link chain that matters. And so if I've got 1 millisecond there instead of 8, which 4G LTE can easily potentially do now, but if I've got 1 there instead of 8, then I have to step back and say, what about the rest of my chain? It still may not be the right solution for me. Because if I need those instantaneous life and death decisions in healthcare, in oil and gas, in mining, or in any other kind of scenario where I've got to stop something that if it continues, it's going to be very problematic and possibly result in health issues, then what I have to do is remove latency. I have to do it right at the end device. And this is why edge computing is so important. So when I'm looking at where things happen, I have to figure out where they need to happen in my wireless solution. I ought to know this information so that I can give the right advice to the people that are, maybe I'm not managing the cloud, maybe I'm not even accessing the cloud. Someone else is doing that, someone out in the manufacturing plant, someone out in the mining field, or someone back at headquarters. But I need to help them make the right decision as to where things need to happen, and I'm the one who should have the understanding of these latency issues. So it becomes a very important thing to consider because latency is, when it comes to the network, I can't get rid of it, but I sure can remove it by removing the network. Now, let me be clear, I'm not saying this is no longer a network device. I'm simply saying it makes those important instant decisions locally. Or, if it doesn't have to be that instantaneous, it could be made in the gateway or on some other on-premises solution. But the point is that I need to look at how much delay can be incurred, and I can still make the decision and take the action in the time frame that's required of my system. So as we look at wireless sensor networks, IoT solutions, and things like this, this becomes an issue that's way more important than it ever was with Wi-Fi laptops, tablets, and mobile phones. We think voice over IP was important, because we were worried about maybe somebody having choppy audio when they were on a phone conversation. Well, choppy audio, I won't say it never killed anyone, but I will say that it's not nearly as dangerous as automated vehicles that are controlled through wireless devices and sensors that need to make immediate decisions related to those vehicles and what they do, or aircraft, or health monitoring systems, or any other such device. And so in those cases, we need to think very clearly about edge computing. Now that does become a challenge too, because a lot of these edge devices, they basically have a Commodore 64 processor inside of them. I mean, that's what surely they would use. It was the best processor in the history of computing, so they probably have that in there. But the point is they've got some very low power, low capable processor, generally speaking. So then the question becomes, how much can I actually do at the edge? And it also becomes part of my decision in the wireless sensors that I select. Because if I need to do more at the edge, I need to make sure I have the processing power to do that at the edge. So all of this becomes important. It's no longer a simple solution or question of, well, that device has the sensors in it that I need, so let me use that device. But rather I have to ask, okay, it's got the sensors, does it have the processing capability? Does it have the application logic and intelligence to actually do the rest of what I require? Oh, this was like right back in this area here that I heard. Oh, you're all confident it was back there? All right, go ahead and stand. Here's our next gift. He's being shy. He was not shy when he shouted too, was he? All right. The second thing you need to know. Dirt is dense, and dense dirt is denser. Think you can say that 10 times real fast? Dirt is dense, and dense dirt is denser. This is a big important thing going on right now in the wireless sensor world. In agriculture and environmental monitoring, there's a lot of in-ground mesh network desires. So there's this desire to put sensors down in the ground and have them connect to each other in a mesh-type network. Well, I don't know if you realize the attenuation levels of dirt, but they're pretty high. And so it becomes quite a challenge. And of course, dirt that has been loosened and is on the surface that someone just dumped out of a dump truck or a loader has a different density than dirt that is packed in the ground and also contains moisture in it and other materials as well. So the density of soil determines in-ground propagation if you're moving from one sensor to another that are both underground. And what we're finding is that at 2.4 gigahertz, you've got about a half a meter. So if you want to do a mesh wireless sensor network, you either have to figure out a way to really crank the power to ridiculous levels, or you've got about a half a meter. And that means you need a mesh device drilled down, dropped into the ground every half meter. If you go to 900 megahertz, now you're dealing with about 3 times that in most tests that have been done so far. About 1.5 meters of range. Hey, that's a lot better, isn't it? It's 3 times bigger, but it still requires an awful lot of mesh nodes. And so the interesting thing, too, is that what we found is deeper is better. Now, that seems to be contrary to intuition, but it is up to a certain limit. Eventually, you get below the topsoil, and when you get below the topsoil, you're getting to even denser materials that are even worse for propagation. But as long as you're deeper in the topsoil, to a certain extent, not beyond the halfway point, but at or just above the halfway point of the topsoil, you end up with better propagation. And the reason is most of these in-ground sensors are not MIMO. They are SISO, right? And what's one of the problems we have with SISO? On the surface even, okay? We've done it, single antenna systems, 11B, 11G, right? What's one of the problems we have with that? Multipath, exactly. Well, what you may not realize is that in an odd phenomenon, when you drop a sensor underground, all of a sudden those RF signals reflect off the surface back into the ground. And so the surface itself becomes a reflection factor that causes the signals to reflect back and end up creating multipath within that network. And so we have this challenge of multipath. So if we go a little bit deeper, we get to a point where the multipath is not as bad. And if we're very strategic about it, and it's going to give us the measurements we need at that depth level, we can strategically place them at locations where we're statistically more likely to get some upfade from in-phase arrival of the multiple paths. And so there are a lot of things being done in this area right now, in agriculture and so forth. But here's the thing. When you're doing in-ground mesh, you don't have to put the radio in the ground. And there was this assumption early on. It's like, well, okay, we've got to drill these holes. We've got to drop these things into the ground. And then suddenly someone realized, well, wait a minute. What if we have a return to surface network? They started calling it an RTS in a lot of these projects. And we can return to surface and actually do the wireless transmission at the surface, but the sensors are underground. Oh, well, that makes sense, doesn't it? Now, all of a sudden, we have much better range. Our cost goes way down because we don't need 1,000 mesh devices to cover a space, but instead we can cover the space with maybe a few dozen if it still gives us the metrics that we desire. So why am I talking to you about this? Well, I'm talking to you about this because materials matter, right? The materials in a space matter. And you know what? Dirt matters too. I'm tired of people not realizing dirt matters. Dirt is important. And so we have to make sure we're measuring our dirt effectively. You know what I'm saying? Whoa, somebody really put some energy into this over here. We got to go over here, Lex. Way over here. I heard a lot of energy there. All right. Now, speed is not always the highest priority. I wish a few people were in the room that I had a conversation with this last week were here because we talked about how we hate capital not. So I put it in the slide, but I don't think any of them are in here. But at any rate, speed is not always the highest priority. This has been something that we hear continually, right? It seems like over the years, just take Wi-Fi, for example, 802.11 prime, 1 or 2 megabits per second. Then we get 11B, 11 megabits per second, and 11A, 54 megabits per second, eventually G and 2.4. Then we get 11N, and we can go up to potentially 600 megabits per second if we ever had the 4 spatial streams. And so it was always about it's getting faster. Then 11AC comes along, it's getting faster. Can someone tell me the name of 802.11ax, not what the Wi-Fi Alliance says? The actual name of the 802.11ax-Fi? High efficiency, right? So remember what we had? We had high throughput and then very high throughput. And you might remember a few years ago I said I was worried that the next one might be very, very high throughput. But thankfully it wasn't. It became high efficiency. Now they do add higher data rates. You know, they had higher QAM modulations and things like that. So they do add higher data rates. But the primary focus has been on being more efficient in the way we use that network. And so speed is not always the highest priority, and some of these modern developments, even in Wi-Fi, do reveal to us that it's not always the highest priority. Of course, we know that speed comes from modulation, coding, channel bandwidth, SNR, SINR, spatial streams. You've heard all of those things in the Wi-Fi world, and guess what? It's not any different in other wireless worlds. It's the same thing. Wireless uses modulation, right? Wireless uses coding. Wireless has a channel bandwidth. It has a signal-to-noise ratio. It has possibly multiple spatial streams in some other technologies as well, such as cellular. And so the point is that all that stuff we learned in Wi-Fi applies to other wireless technologies as well, but the reality is the speed's not always important to us. Sometimes we want a low-rate connection because we're in a noisy environment, and we need to have lower SNR because we need a link there. It's noisy, and we just need the link, right? So we live with lower data rates. Sometimes it's because we want longer range. So the farther we get away from the two transceivers away from each other, obviously, the lower our data rates are going to be. Assuming it's a system that can adjust data rates. Not all wireless technologies do data rate adjustment at all. Some of them either have a link or they don't. And the link is one fixed rate. Others of them have a fixed rate that's high, and then they drop off to a ridiculously low rate, and there are only two actual rates that they use. So it varies by technology, but long-range communications generally means lower data rates. And then maybe there's just limited frequency bandwidth available. So I'm intentionally using a narrower channel. You know, some technologies were actually designed intelligently enough to allow you to go smaller and not just bigger. Don't you wish Wi-Fi did that for you? You know, which of course it's finally doing, right? With 802.11ax. But for so many years, it's always been about let's go bigger. Well, okay, we went from 22 megahertz to 20 if you count that. But other than that, it was 20 to 40, 40 to 80, 80 to 160. How big can we make these channels? All the time we're saying what we need is 10 megahertz or 5 megahertz. Let's go down. And that's the beauty of a lot of wireless technologies. They're very flexible in this. You can have a 1 megahertz channel, a 5 megahertz channel, 10 megahertz channel, 20 megahertz channel. So you can adjust the channel width to what you need, and that's very useful when you have low frequency bandwidth available. Or the way I like to say it is this: if your technology allows you to use a narrower channel, use the narrowest channel that meets your need every time. Because if you use the narrowest channel that meets your need every time, you've just left yourself space for the future. But if you use the wider channel because you said, well, I'm going to get these bigger data rates, I might as well get it even though I'm only sending 1 kilobyte every 30 minutes, then you've hurt your space and you've used more frequency than you need unnecessarily. Yeah, the airtime utilization thankfully won't be high, but if you made that decision with 100 devices and now you're bringing in 100 more, and then 100 more, and then 100 more over the years, you've used up your frequency space unnecessarily. So use as little frequency as you require to get the job done. That should be the goal. Now, when we think about this, that speed is not always the highest priority, then other things may end up being the priority, right? Range is one. So range might be a priority. For example, we have here what's called a water rope sensor. And a water rope sensor actually is just what it sounds like. It's a rope that senses water. And so you could drop this rope down into a tanker. You can usually get them for even lengths up to 100 feet or so. Drop it down into a tanker, and it's going to tell you when the water comes up to the level where it touches the rope because it effectively closes the circuit in the rope. And when that happens, it detects there must be water there, the circuit is closed, and then it's going to communicate that back to the gateway. So these particular sensors here happen to be from one provider that has a proprietary protocol, but the solution can go up to 1,200 feet without direct line of sight necessarily. Or for those of you that I do love internationally, and that I agree with you, we should be using 366 meters, roughly. You're welcome. Now, speed is also not the highest priority sometimes because resiliency is. The more important thing is having the ability to get a communication through than being able to get it through fast. And mesh works well for this, and there are a lot of mesh technologies. The simple fact is, if I implement mesh instead of a single direct link, then there's a pretty good chance that my mesh is going to be slower than my direct link would have been, because I'm adding latency in the hops, right? I've got both processing latency and link latency, all of this along the hop. So it's going to slow it down if I add a lot more hops, but it's going to give me resiliency. So we see here an example of the newer Bluetooth mesh that's beginning to gain in popularity, and some other mesh technologies as well. So speed is not always the highest priority. Sometimes it's resiliency. Speed is not always the highest priority. Sometimes it's about battery life. Sometimes it's about making sure that my battery lasts as long as I can get my battery to last. 5 years, 10 years. Some people promise 25-year battery life. I really do hope to be able to implement all devices with 25-year battery life, because then I never have to touch them again, because I'll be retired and there's someone else's problem. But most of them don't go that far. Most of them will go up to 10 years, and it's going to depend on all kinds of factors. It depends on the quality of the link. Do I have a good link so that when I send the data, it works, so I don't have to send the data again, right? So every time I have to retry, I'm consuming more battery. So the quality of the link becomes important. But it also has to do with the components. So what kind of radio am I using? A low-power transmitter is low power because it has low output power, right? So the lower output power it has, the lower power it consumes, is the general theory. It does depend on the architecture, but in general, the lower power it radiates at, the lower power it consumes. So the consumers are the radio components, the CPU or ASICs, if there's local storage in the device. So, for example, a wireless sensor might have storage so that it can keep sensed data for some point in time when it's going to transfer that information later, rather than transferring it in real time all the time. Or if the gateway becomes unavailable for some reason, it may temporarily store it for some period of time until it can translate it when or transfer it when the gateway comes back up. So they may have local storage. We need to think about that and the power it'll consume. Then there are wired ports that might be in the device. So maybe they do have an Ethernet connection or something of that sort, or even other types of wired ports like USB and so forth that might be connected to different components. And then, of course, any other interface. So every time you add a chip or a component, you're probably adding some type of power consumption. And this is one of the reasons why when you're building IoT devices, if you want them to run off of battery, you don't want to use more than you need. So you don't want to go out and get like a Raspberry Pi 4 maker board because, hey, it's got all these cool features and if I ever need them, they'll be there, when you can get a much less power-consuming board that gives you a microcontroller board that's going to get the job done for you. And so you always have to keep that in mind when you're thinking about building these devices, because it's not always about speed. Sometimes it's about extending that battery life and making it last as long as we possibly can. Oh, this is a tough one. I'm going to let you all decide. Point at who you think got it. They're pointing to the back. Okay, all the way back in the back, Lex. White hat. Is that a white hat? Looks like a white hat to me. That's good, because if it was a black hat, we'd be watching you. All right. Successful wireless solutions do not equal good RF alone. So I started into this morning when I first started. Solution. Pronounced solution. All right? It means solving a problem or dealing with a difficult situation. Have you ever had to do that? If you have, you're a solutions expert, right? So you know how to create a solution. A wireless solution is not just about the RF link. It's the end-to-end solution that gets the business results desired. So a successful wireless solution is not just about good RF. It may include any of these components as well. Yes, it might have the wireless. It might have some programming. It might have some database decisions that have to be made. We might have some APIs that we need to access. We might have to decide whether we're going to be in the cloud or not. All of these things. And yes, it might even be an AI factor. It really might. Because even though we like to make fun of AI when people announce that they have AI, the reality is, whatever they're calling AI, if it's beneficial to me, I may need it, right? So even if we disagree on whether it's truly AI or not, maybe we should stop asking that question and ask, is it something I need? Is the thing they're doing something I need? Because that's the real question. We really don't care what they're calling it. They might call it AI, and it might be AI. They may call it AI, and it's not AI. But whatever it is, does it solve my problem? And if it does, that's something that I need. And so we have to do that interpretation. If there are vendors in the room, hey, thank you for giving us simple words to understand what you're trying to explain to us. But in the end, we have to make the decision on the actual thing your product does, and does it meet my actual needs, whatever you call it, whether it's marketing speak or legitimate terminology. But I will say very clearly, an awful lot of AI talk is just talk and marketing speak, and people really need to get a life and quit going there. That's all right, you can applaud that. Or three of you can. So the point, though, is that picking a wireless solution is more than just saying, well, I'm going to use 900 megahertz, or I'm going to use 400 megahertz, or 2.4 gigahertz, or 5 or 6. It's more than that. Picking a wireless solution is about looking holistically at the entire thing and making sure that it's actually going to meet my needs. Oh, that was very clear back here, right here. Gentleman raising his hand, Lex. Very good. All right, I'm about to blow some of your minds. I'm sure some of you know this, but I'm going to blow some of your minds right now. When you learn in CWNA about how the 802.11 standard is updated, you learn that it's updated through amendments, right? It's what we teach. And it's absolutely true. It's updated through amendments. But not all changes come through amendments. How many of you have heard of the maintenance task group? You ever heard of them? Like 4 of us? Maybe I should just give all the rest of the gifts to them. The maintenance task group is currently on maintenance D. Okay, so that's where they are right now. It'll be our next 802.11- some year when it's done. So what you see is 802.11 2016. That was the 802.11 TGMC. When you saw 802.11 2012, that was the 802.11 TGMB. Okay? So this was the task group maintenance B, task group maintenance C. Now we're under task group maintenance D. Now, this was, I read these things. I don't know if you guys do. I actually read these things. I go out and I read these minutes from the meetings, and I explore the changes they're considering making, so I kind of get a heads up for what might be coming. This was my absolute favorite that I found in MD so far. The comment was based on clause 11.1.4.3.4. Yes, we have even deeper. And the comment said there are too many double negations in this paragraph, making it hard to follow. For example, shall not respond is not a mesh station, and none of following are met. So that was the example. They proposed a change. Let's reorganize the paragraph to remove double negations. The resolution, rejected. The negative style of this subclause is necessary, even if harder to read, to create clear shall or shall not requirements and not a may statement, which is less clear about specific requirements. Further listing specific rules for why the station shall not respond here avoids any confusion with requirements elsewhere in the draft that have additional reasons that a station shall not respond. How many of you understand that resolution? I think it has too many negatives. It was funny because it makes me wonder if the person that wrote that rejection comment was the same person who wrote the section that was being challenged, because it kind of, when I went into 11.1.4.3.4 and I actually took a look at what it said, it read a lot like that rejection notice. And so these are interesting. Now, my favorite all time in these maintenance group documents, I've shared with some of you before, I know, because you've been to class when I shared it. My absolute favorite of all time was when one person said, every time I look at Annex J, I just want to kill myself. It shouldn't be there. The response was, the individual commenting on Annex J should either have his desire met and have the annex removed, or he should be placed in a straitjacket. That was literally in the documentation. I loved it. It was one of those moments where I thought, okay, these guys can have fun too. These gals can get it on and have a good time. So I really thought that was funny. All right, so this is the one in process right now. But let me share with you something real world. All right, fine timing measurement. How many of you have heard of FTM? Fine timing measurement. Okay? A lot of people never heard of it because guess what? There was no amendment that gave it to us. And if it's not an amendment, we don't hear about it. If it's not 11B, 11G, 11A, if it's not 11BZ, 11ZZ top, or anything else like that, we don't even hear about it, right? This came out of 802.11 TGMC. When they were creating 802.11 2016, there was no amendment. This is an entire concept available in 802.11 whereby a station can actually determine its relative distance from the access point within to around a meter. And so it's based on specific FTM frames that go out between the AP and the station, the AP, and they measure the time of departure from the antenna with some predictive information that says how much longer from this very moment right now is it going to be before it really leaves the antenna. So when the preamble departs from the antenna is the first measurement. Then when the preamble begins to arrive at the receiving antenna is the next measurement. And then on the response, when the preamble begins to depart from the antenna and when it begins to appear at the receiving antenna. And so based on that information and time of flight calculations, we can do some estimation of distance. And so this is something that's built right into the 802.11 standard. It did not come from an amendment. Instead, it came out of the task group. So why am I telling you this? I'm telling you this so if you are trying to follow what happens with the 802.11 standard or other standards, 802.15.4, whatever, it's important to know that there are a lot of people out there that mess with you and sneak some pretty cool things in without making it part of an amendment. And this is one of those examples of something pretty cool that made its way into the 802.11 standard. And there even are some chipsets out there that support it amazingly, right? So, interesting. I believe we might have someone from Europe. I'm not sure which one. You guys want to fight it out? Martin said no real quick. Is he afraid of you, Anders? He's too big. All right. Anders right up here, he has a gift. All right. The stuff in the space matters. Now, how many of you have heard of wireless HART? Any of you heard of wireless HART? All right. One of the industrial IoT protocols commonly in use out there. It started actually as the HART protocol, and it was used in industry on wireline communications and links, but then they implemented a wireless version of it. And in evaluations that have been done so far, we found that with heavy obstructions, that would be very large machinery and aisles so small that pretty much just people can go down the aisles between the machinery, that they can get about 100 feet, or remember, because I love you all, 30-ish meters. See, that's my West Virginia conversion from feet to meters, 30-ish, okay? Medium obstructions. Now, this is when the aisleway is large enough you could probably push a large cart down it. The machinery is a little more spaced out on the floor plan of the plant or the manufacturing environment, so there's a little bit more breathing room. You can get up to about 250 feet of range with this. And by the way, wireless HART is generally implemented as a mesh technology. So we're talking about links between mesh devices. If you have light obstruction, then you're looking at around 500 feet. With light obstruction, we would define it as you could pretty well drive a truck between the machinery. It's that far apart, okay? So there's big gaps, more airspace. And then when you've got clear line of sight, 750, 800 feet, 230-ish meters or so is the range. Now, the reason this is important to think about it from this perspective is because your devices are not up here. Your devices are down here. And there are these mesh devices that are attached to machinery, attached to various components in the plant, and they need to communicate with each other. So they don't get to shoot over things. They've got to deal with where they are on the floor. And so they're not necessarily connecting, in other words, to something that might be deployed above them, like an access point would be with Wi-Fi IoT devices or something of that sort. Instead, they're building the mesh throughout the plant and then eventually going to some sink or gateway at the edge of the mesh. So the stuff in the space matters. Brett Hill, are you in here this morning? You are? I've got one right here just for you, my friend. Alpaca manure, it sells. Brett, I don't know if you know this, but if you go into the business, it attenuates. So those solar-powered wireless devices you've got all along, they're not going to work the way you expect them to anymore once you get these piles of alpaca manure. I just wanted to throw that in to make sure you were thinking about that during your deployment of this new business enterprise you're going into, okay? Just my free consulting tip to you. Oh, I heard that S was wildly clear from right over here. Where was that over here? Okay, go ahead. Right here, Lex, is our next one. By the way, if you win one, don't yell out again, you little greedy thing, okay? All right, AI isn't necessarily magic. In fact, AI isn't magic at all. People ask me a lot of times what I feel about AI, what I think about AI, and I've been in love with AI since I was like a kid, and I was like a kid because I was never really a kid. I was just kind of like a grown-up in a little kid's body. But when I was like a kid, I was in love with AI, always have been. And it wasn't because of movies. I'm a weird human being. It was because of books. And I was reading at 8, 9, and 10 years old. I was reading books on artificial intelligence and computing technologies, and that was thrilling to me. And my wife right now is back there saying, I wish he'd just shut up and move on. What's that? Yay books. There you go. All right. So loved reading. And so AI has kind of been an interest and a passion of mine all of my life. And what I've come to the conclusion of myself for me is I can define it simple. It's just algorithms on algorithms on algorithms. And there's a very simple reason for that. The only thing a computer can do is process an algorithm. That's it. It can't do anything else. All it can do is process an algorithm. Therefore, if a computer's doing it, it has to be an algorithm. Therefore, AI in a computer, it's algorithms. That's what it is. Now, they can be really complex algorithms, don't get me wrong, but they're algorithms none the same. And those algorithms give us the illusion of intelligence. They don't give us intelligence because, let's just be honest, folks, pat someone on the back, give the credit where the credit is due. The intelligence is with the programmer who wrote the algorithm. That's where the smarts is. Even if it's a learning machine, the intelligence is with the program who wrote the learning algorithms. That's where the intelligence was. That machine is still just obeying the commands that were given to it long ago. Even if it's changed its behavior somewhat based on what it's learned, it's still doing nothing more than obeying commands it was given long ago. It always goes back to the original algorithms. So don't let AI overwhelm you. The next time someone says to you, well, our wireless solution uses AI, ask them, what's the algorithm? What's it actually doing, in other words? Don't just tell me, well, this device can determine which clients on your network are associated with the wrong AP, and it can then utilize these methods or that method to get it to move to another AP. All right, how are you determined they're associated to the wrong AP? It's an algorithm is all it is. Most of these, by the way, are really just expert systems. They don't really fall into the full category of artificial intelligence, but still, it's an algorithm. So how are you making that decision? How are you determining it should move? Because that's going to help me decide whether I think that that feature should be turned on or not in my deployment. Because I'm the one that needs to decide whether you've actually chosen a good algorithm. We're over here. Is it the far corner, I do believe? All right, way over here in the far corner. We're getting close, aren't we? This is number 8. Hey, smarts aren't always at the edge. So I've already talked about this. I'm just going to talk about it for a little bit more. You have to think about where you want your compute to take place, where these algorithms are going to happen. And the way to think about it in general is if you need faster control speed, you're closer to the edge. If you need more processing power, you're further up into cloud-type technologies or data center technologies. So when you think about it, when you think about the cloud, it's, I don't know where they put that. When you think about the fog, it's, I don't remember where I put that. And when you think about on-premises, it's, I don't really know who's in charge of that. And when you think about on-sensor or on-device, it's, I'm not really sure it can do that. So this is the way you kind of think about it, because that's what you're dealing with at each level. In the cloud, I don't know where they put that. So what's the big obvious concern there? Security, right? I've got to make sure they're implementing the right security solutions to protect my data if I'm going to use the cloud, because I don't know where they put that. In the fog, I don't remember where I put that. Well, the fog is kind of foggy right now, so maybe just don't use the term fog and say somewhere between the cloud and my network and decide where it actually is and just define it. That way you won't forget. On-premises, obviously, is an important thing, because now all of a sudden our latency has been reduced to a very minimal level. And so when it does come to the need for faster control decisions, but maybe not near instantaneous, we might be able to get by with just on premises. And then finally, on the sensor or device. So it doesn't always have to be at the edge, on the sensor or on the device, But it has to be somewhere, and we decide where that's going to be based on how much processing power we need and how quickly our decisions need to be made. These are the key factors. Wow. I almost want to give it to Jason for just how late he was. Everybody else was done, and then he says 9. That was good. Okay, it was definitely over here. Does anyone know who won that one? Right over here? All right, right up here, Lex. Very good. All right, new rule. You ready for the new rule? For the next 2 after this, only the women, because women matter. All right, there you go. Now, here we go. Number 9, wireless devices can be powered by more. You know, how do we power our wireless devices and Wi-Fi networks? PoE or magic. PoE or we plug it into the wall, right? That's how we power them. And so the reality is, PoE is like so last week. Energy harvesting is what's cool, okay? So what does that really mean? Well, obviously, this is the one we all think of, right? When we think of energy harvesting, we think of solar power. That's one way that we can do energy harvesting. We've also got wind energy. And when we think of wind energy, we tend to think of the big, giant windmills on the hills, you know, up in Chicago and all over the world in different places. But what about the little ones on the top of light poles that might be supplemented by solar panels as well? So we're using 2 types of energy harvesting at the same time. In this case, it's just to power the light, but it is a smart light. There's some circuitry in there. There's some network communications back to centralized control. And so the point is, I don't have to run a power line to the pole. I'm going to harvest energy from the wind and from the solar, store it in batteries, so that at night, I've got my power, right? And then on the left side, we actually have a BLE sensor. Brilliant. I mean, who didn't think of this? Why not power a wind speed detector by creating energy from the wind speed that's being detected? Makes a lot of sense, doesn't it? And that's exactly what this device is. So it basically takes advantage of the wind, moving it around to generate the power for it to be able to do its work. Energy harvesting. Then we have many other sources, okay? So you can harvest energy from light. Some of you might have had the keyboards, you know, that you need to have them in a room with the lights on and they recharge themselves. Any of you had those? Like Logitech made one. I know a few others have as well. And as long as the lights are on in the room, it'll harvest energy just from your lights and recharge the batteries. I know that because I left it sitting in the garage for a very long time in a box, and then it didn't work anymore because it wasn't in the light. You can obviously harvest from sunlight. We have thermal harvesting, different types of heat, like alpaca manure, or put your keyboard in. You only need about 2 cubic meters of alpaca manure to power an IoT device. Okay, so new business opportunity for you, Brett. Sell it to all those people powering their agricultural devices. All right, so any source of heat can be converted into energy. Vibration, you know, the vibration causes movement. Movement can be turned to energy, right? So this vibration can come from all kinds of sources, nearby motors that happen to be running anyway. They can be, when the trains go along the railroad, and the vibration actually generates energy that can be harvested into batteries and used to power rail-side IoT devices and sensors. So vibrations can be used. One that's not listed here is flow harvesting. So you can have devices that are in the piping that as the water or oil or whatever flows through it, it causes motion. And since there's motion that's being caused, we can harvest energy from that process. And so there are flow-based energy harvesting solutions as well. And of course, RF, pulling energy from RF that's in the air, right? So, you know, when we talk about receiving an RF signal, well, that had to be transmitted, right? When it was transmitted, what did we generate? Energy. So when we receive it, it's energy, just a whole lot less at the point of receiver. But we can still harvest that energy. And not necessarily harvesting it from a single signal we're intending to receive. But did you know there's other signals in the environment? around you, the stuff you don't even care about right now. There's all kinds of RF energy around us. And so we can harvest that. Energy harvesting is becoming very, very, very big, especially in the outdoor wireless IoT, wireless sensor networks, things like that. There's an organization called Ocean that's strictly what they focus on, is building energy harvesting solutions like this. Oh, it was over this way, somewhere. Over here, right over here. Lex, all the way toward the front, right by Tufik, our speaker from Wednesday. Great job, Tufik. Thank you. Now, number 10, if you can't buy it, as I'm coming to a close, you can make it. Now, interestingly enough, I told you earlier, don't use these types of devices if power consumption matters to you. But if you can power it through PoE or through wall plug power or large batteries or something, then something like this might work for your solution. Now, I'm not encouraging and never would encourage someone who's going to sell the thing they make to make it out of these devices. Unless you're planning to sell in low volume and then be prepared to re-engineer everything every couple of years. Because being able to get a certain model of these devices in 2 years might be challenging. But if you use a microcontroller board that is currently in inventory in the hundreds of thousands in just one reseller and possibly tens of hundreds of thousands around the world, then guess what? You've got something that not only is in volume now, but you've got something that's probably going to continue to be in volume for some time. And you can even reach out to those resellers and ask how long they'll be able to provide it to you, get a contract so they can provide it for some period of time to make sure you can continue manufacturing to whatever spec you develop for now. So if you're going to be reselling, I wouldn't go this route. But if this is for you and you've got a 1-off or 10-off or 20-off solution that you need to build for your environment, it's not actually that hard to do with devices like this. This gives you your intelligence of a computer, and then you simply need to plug in the right extra components, sensors, wireless modules to communicate with the type of system you want to communicate with, and so forth. In fact, when we launch our CWCP class next year, we'll actually be building IoT devices from components, though it will not be these components. We're actually going to build one like someone would build that was going to sell 20,000 units every 6 months. Although you're not going to build 20,000 units, don't worry. It's not free labor for CWNP starting a new line of business. Okay. You are not a woman. I'm just... Or maybe you are. And that's okay. So you just let me know. And I'll have another gift for you later if it was true, okay? So I believe we had right back here in the back. Is that right? Okay, very good. All right. Everyone give a hand to all those that got a gift today. All right. Now finally then, if you can make it, you can connect it. You can get modules for all the different protocols that we talk about in the CWSA course and that we'll explore more in CWCP. All of those modules you can acquire. So if you wanted to do LoRa communications, even build your own gateway because you're just that cool. If you want to do it, you can do it by just getting LoRa modules. So the LoRa protocol, the modulation that's unique to LoRa, works only on that wireless link between the end device and the gateway. After that, it's the LoRaWAN protocol, which is not wireless at all. Okay? So it's really just a protocol for how communications get across other carrier networks to get to larger network distributions. So the module gives you that radio link. You can get a Zigbee module. You can get a Bluetooth module. If you're going to get a Bluetooth module and play around with it and start learning about that, make sure you get at least a Bluetooth 4 or newer capable module so that it's BLE capable, but preferably one that's capable of Bluetooth mesh and so forth, so that you can really play with all of the new cool features in the latest Bluetooth specification. And yes, I know some people in some companies must find this a challenge to believe it's real, but you can get a dual band Wi-Fi module. They make these things. You can put them in a device that you manufacture, so it doesn't just work on 2.4 gigahertz. It's dual band. I was so astounded. because I thought they must only be 2.4 gigahertz modules out there that are available because everybody's selling these 2.4 gigahertz only devices. But no, they make dual band modules, people. It's a miracle. So let your vendors know, let the people that make your grill know, let the people that make your hair dryer that's got Wi-Fi in it know, whatever it is, that they make dual band Wi-Fi modules that are pretty inexpensive. And so they do have them. Whatever it is you want to communicate with. And these are just a few examples. There are many other protocols out there. But you can get modules that you can plug into your microcontroller boards. And then you can get sensors that you plug into your microcontroller boards. And you can build a solution yourself. And here's what I'd challenge you to do. Start playing with this stuff. It's not that expensive. You can go to digikey.com, for example, and you can buy all the parts you need to build a basic wireless sensing device for under $100. You don't really have to spend a whole lot of money. So you can build a basic wireless sensing device, build your own. So the next time you think, oh, it'd be cool to have this new smart home technology, build, don't buy it. Learn this stuff. Understand how it works. Have some fun with it. And then plus, the next time a boss or somebody else comes up to you at work, or maybe it's in a company that you're contracted with, and they say, hey, do you know anything about this? Why, you know what? I built all my own at home because I'm running LoRa and Zigbee and Bluetooth and Wi-Fi and all of this because I wanted to play with all of them. It's not that hard to do. You can do it too. So make sure you explore these different solutions that get you connected. And with that, I just want to say thank you for listening to my 10 and a half things. And before we take a break here, bring Joel back out to put us on break, let me say also, thank you very much for having a little bit of fun with me this morning. I enjoyed the process of giving away the gifts, and hopefully you enjoyed it too. So thank you very much.
Joel? Do you want to take questions or anything?
Sure.
When you were talking about little boards and stuff, one thing I'll say is, like on the packet potato, this is an ESP8266 on a Wemos D1 Mini. It's like, for some of you, it's like Greek, like a what, you know? But some of you probably recognize that little chipset. The ESP8266 is super cheap. I think this board I got these for $3 each on eBay. They're incredibly cheap, and they're actually really easy to develop for. I'm not a software developer at all, and I'm barely touching what this little guy can do. It can do a lot more than I'm doing with it, but if you need to build some specialized hardware, I mean, it's out there. Electronics prototyping has gotten really, really easy over the past few years.
And let me ask a question, based on that he's talking about. How many of you think it would be kind of fun to have a wireless badge next year? Not this one, because this is trademarked.
It is?
But a wireless badge that you could play with during the conference and see what people can come up with. Would that be something you'd be interested in? Cool. All right, cool. Excellent.
Yeah, cool. Well,
okay.
Yeah.
Any other questions? Right over here.
I'll bring the mic down.
Yes, what is that link again, Femi? cwnp.link/growth. Later on today, we'll be giving away a free pass to next year's conference, and it's going to go to one lucky person that filled out the survey. So cwnp.link/growth. Thank you for the reminder.
Any other questions or comments or anything like that for Tom before we move on?
All right, thank
Cool.
you.
Awesome. Thank you, Tom. Okay, so we're going to get set up for our next discussion here. So we're going to take...